Okay, so this is my third video on module theory. Recall that last time I briefly discussed about the notions of modules, what is a submodule, module homomorphism, etc. And also I discussed about free modules. So I'll come to free modules later in one of my other videos. So for now, just as well. For now, just I think it's. I don't think you need anything more to understand whatever I'm going to be talking about in the next one or two videos. So I think the only you need to know what is a free module. That is a module having a basis. That is a generating set that is also linearly independent. The same exact thing about vector space. So yeah, and then I stop the lecture by saying what is a direct product or direct sum of modules, right? So I discussed those three equivalent conditions if you remember. So yeah, so this was those equivalence conditions. So you will write this direct sum of this M1 to Mn like this. Okay, so yeah, now, so as I said, today I will be talking about what are exact sequences, short exact sequences, what is split exact sequence. So I'll briefly uh, talk about these things. So let us begin with what is an exact sequence. So suppose you have a collection of modules and homomorphism between them. So let me write them in this way. Like you have this is the zero module, then you have a map from this to a module A, then to a module B, then to a module C, then D, and then say E, and then 0. Okay, so the maps are this is the usual map because there is no other choice, and also this is the usual one, so I'm not writing. So suppose this is F1, that is F2, and that is F3, F4. So this is so each if from A to E are modules over say a ring R commutative ring with identity, and you have this homomorphism between these modules. So this collection of modules and homomorphisms is said to be exact if so. Firstly, exact at where? So exact at say B. Okay. B if so. Observe that exact at B. So I'm talking about at this position. So here, what are the two things that we have from this diagram? You have that image of F is a submodule of B as well as kernel of F2. So if both are same, then we call it exact at B. And similarly, if it is exact at C, then the image of F2 will be same as kernel of F3. So this is exact at B, and this entire diagram is said to be an exact sequence if it is exact at each point. Like at A, it is also exact at B, C, D, and also at E. So this is said to be exact if kernel of Fi plus 1 is image of Fi for I 1, 2, then you have 3. Yeah, so we have the 4. And moreover, what does it mean if we say it is exact at E? It means that kernel of F1 is the image of that map coming, the map which is denoted by the circle 1. But that is the zero map because there is an only one element in the domain. So kernel of F1 to be the sequence exact at A, you need to have kernel of F1 to be 0. That is, F1 must be injected. And similarly, the other endpoint, the exactness as E means that the map going into E, that is F4, should have image same as the map from E to 0 have the kernel. So what the kernel has to be the entire set E because that is just a 0 map. So you need to have image of F4 to be exact at the position E. you need to have image of F4 is same as kernel of that map, which I denoted by 2 within the circle. So that map has kernel entirely. So that is this. So it means F4 is on. So yeah, this is the definition of what is called an exact sequence. And in particular, if you have this type of exact sequence, say you have three modules, you have 0 to A, to B, to C, to 0, with the usual homomorphism being exact at each of those A, B, C, then it is called short exact sequence. Short exact sequence, and we will write it as SPS. Okay. So, as I said, from these two observations, you see if this is exact, then clearly there is an isomorphism between A and B, right? Because the map from A to B is both 1, 1 and on. Okay. And now, secondly, I want to define another thing, what is complex. Complex is somewhat weaker than what is an exact sequence, because to need like to be exact at a point, you need to have the image and kernel both are exactly same. But when we talk about complexes, suppose then you need, say, a chain of modules which I'm indexing by the set of natural numbers. So let's just take it as let's just take AI plus 1 to AI minus 1, and so on to 0. So there are infinitely many modules, and you have these maps. Fi plus 1, then Fi is said to be a complex if you apply the map F twice, you will get 0. F means I'm just neglecting the indices. So if you just write it properly, we get, if you apply Fi plus 1, so you will land inside AI. And then if you apply Fi, you will land inside AI minus 1. But if it is to be a complex, you need to, this is 0. So if you apply the consecutive two FIs, then you will get 0 at all the stages. So this should hold for every year. And in other words, this is same as the image of Fi plus 1 should be entirely contained inside kernel of Fi. So that is why I said this is somewhat weaker than what is the exact sequence, because exactness means both of them have to be exactly same. But here one of them is just contained in another. So yeah, so this is just a complex. Now, how do you make how do you produce an exact sequence? That is the main question. This is all fine for like subjective thing, but how do you produce an exact sequence given a module? So one thing is for sure, you can just take the, say, if you have say you have a homomorphism from M, or I should say if you have a submodule in of M, suppose there is, M is not a simple module. Simple module means there is no other submodule other than the trivial one. So if N is not simple, then there exists a submodule, right? And with the submodule comes the natural projection from M to this. And this is a surjective mode. So you can extend it to 0. And this is exact, right? That is obvious. But you can extend it to the left side as well by just taking, say, you can take the kernel of phi, which is inside it. So this is just the natural inclusion map. So this map has to be injective because this is an inclusion map. So you can again extend it to 0 from the left. So you get that first of all this is injective. So exactness at this point is no problem. Again this is surjective. So exactness at this point is again no problem. And say call it I. This is pi. So what is image of I? Image of I is just the uh, isomorphic to kernel of pi, right? Because this map is the map I is injected. So this is isomorphic to kernel of pi. But again, so that is same as kernel of pi, right? Because this map. So what we need to show exactness at M, you just need image of I to be same as kernel of pi. But image of I is anyway equal to kernel of pi. So that is done, right? So exactness at M is also no problem. So this is an exact sequence. Okay, so you can produce exact sequences like this. Or suppose you have so th- this is a short exact sequence, and suppose you have a long exact sequence. Okay, then you can also break it into short exact like this. What do you do? Here you have this natural projection map to start with. So from that you don't need to worry about anything. Just take the kernel and just inject it into the domain and blah blah blah. But if you have a long exact sequence, okay. For example, suppose you have AI to BI, CI. This is again coming from something, and then you are again coming back to AI minus one, BI minus one, CI minus one, and then you are again it's going like this. Then you can break it into short exact sequences. For example, let me call this method phi I, phi I minus one. This is psi I minus one. So what you do? You just let's see what we can do. Uh, okay. So so let me define one thing: the co-kernel of a map. So if you have a map F from module homomorphism from A to B to module, the co-kernel of F is just the B modulo image of it. This is just a fancy name of this quotient. This co-kernel. So, for example, you can break it in this position. So let me break it. So you have this AI to BI to CI. You have this psi I. You have this phi I. So then what you do is just take so this is coming. So what you can do just take say what should we take? Let's see. So image of phi I is a submodule of CI, right? So again you can consider this image of psi, right? This is again the natural projection map, and because this is subjective, you can add a zero. Now see, exactness at AI is not a problem because this was already an exact sequence. Similarly at BI. Now at CI, this is the image of psi. But again, you know the kernel of a projection map is just this image of psi. So that is again not a problem. And anyway, psi is surjective, so exactness at this co-kernel, let me just write this co-kernel of say phi. Or no, this is actually not the co-kernel because let me just write a co-kernel of psi. Anyway, so it's not necessary to write this. So yeah, this is like this is a way to break long exact sequences into short exact sequences. And again, what you can do, let's see, you can also break it in left side. Like here, I just stop this sequence on the right by just adding this map part, the natural projection. And again, you can stop it in say left side. Let's see how. So, okay, yeah, yeah. So you have this phi I map here, and that is coming from here C, or maybe okay. Yeah, I don't need any other map. So let's just write kernel of phi. That is again a submodule of AI, and this is just the inclusion map because this is inside AI anyway. So yeah, and again you can attach a zero to it, right? Because this is an injective map, so there is no problem if you attach a zero to the left of this sequence. So let's see. So exactness at AI, sorry, at BI, CI, and at this point is not a problem. Now listen, because this map is injective, this inclusion, so exactness at this is also not a problem. And at AI, anyway, you have, as I said in this case, so image of phi that is just same as this map is phi. So both of them again coincide. So you have this exact sequence. So you can break this. There is something called long exact sequences, and I will come to this. What is this? A snake-like map. This is the boundary map sometimes called. Oh, sorry, boundary. This is the attaching map. Sorry. So yeah. So I will come to these things later when I will discuss about snake lemma and all. So for now, you can do. Or again, you can take, say, suppose, or you can take, consider, or maybe let me leave these things for later. Otherwise, it will take a lot of time. So anyway, so this is a what is short exact sequences, and this is how you can break long exact sequences into some sort of short exact sequences because the length of the sequence is finite. And now let me come to what is called a split exact sequences. Or okay, so to motivate about split exactness, let's see about this example. Suppose you have two module M, 0 to M. You have two module M and N. Again, this usual map. Let's just take their direct sum, where this is the x going to x comma 0 usual map, and this is just any x comma y going to the usual projection y. Okay, so clearly this map is, let's just call it F. So F is injective, so this is exact. Again, G is, let me call it, sorry, let me call this map G. So this G is surjective, so this is exact at the position in. And you can easily see that image of F is just the entire X line. Right? If I talk, if you can imagine it with R2, so this is just the X axis, right? The horizontal X axis. But again, kernel of G is again is the same, right? Because you are just projecting onto the Y component. So yeah, anything that lies completely on X axis will go to 0, and hence you get this. So this is a short exact sequence. And this is very natural, right? Just like the projection map and this inclusion map, like if I call this, let's say this is example one. This is very natural. And again, this is also very natural. Right? Natural by natural, I mean the two maps that we are considering here, this FG and also this inclusion and this projection, both of them comes for free whenever you have such a direct sum of modules, right? That is same as usual vector space. So, yeah. Okay, now let's come to what is called the split exact. Split exact sequence. So firstly, it there has to be an exact sequence, right? That is from the name of the definition. So firstly, suppose you have an exact sequence or a short exact sequence of modules, say A, B, C, and 0, then let me call these maps as F and G. So it clearly F is 1 1, G is on 2, and image of F is same as kernel of G. Okay, and now it is this exact sequence. So this is an exact sequence is said to be a split exact sequence. Split exact sequence if so you have this image of F, right? That is inside in B. So this appears as the direct summand of B. What does it mean by direct summand? So if this is a direct summand of B, that means there exists another submodule, say B prime. This means there exists another submodule B prime of B such that B can be written as internal direct sum of this image of F and this B prime. Yeah. So that is what I mean by direct summand because image of F is a summand, right? Because this is one of those submodules that is appearing when you write B as an internal direct sum. So that is what a split exact sequence, and you can equivalently view it like you can equivalently think this uh, definition in another way, right? For example, let's see. So in this second example uh, that I showed, clearly here this is a split exact sequence, right? Because in this, let's just call this module say A, then you have this F is injective, so M is anyway isomorphic to the image of F, F of M. So then A can be written as the direct summand of image of F and also some other module, right? Here the other module is N. That is clearly a split exact. And also, if you look at it from this perspective, there exists another map from the from in to A, from the other direction. So this is just from here to here. What is this map? Again, usual any say in zoom any n goes to 0 comma n. Let's just call this map as G, sorry H, and then you get that G compose H on any say n will give you again n. So that is just identity on, right? So this is in general. So we can define the equivalence or equivalent definition. Equivalent definition. So suppose this sequences. So I'm not writing everything again. So let's just say let's just take it from here. So the following are equivalent. So the first statement is this is a split exact sequence. Okay? That is the important part. So suppose this A to B to C to 0 is a split exact sequence. And the next thing is there exists a map H from C to B in this case, such that G compose H is identity on C. Okay, so let's see the proof. So firstly, assume that this is a split exact sequence. So one is this. This is a split exact. So one implies two. So due to split exactness, you get B is direct summand of this and some other B prime. Okay. And then you need to find a map from C to B. Okay. But again, if you just uh, let's see, so you need a map from C to B. But clearly you have a map. How should I say? one thing you can observe from the definition that is clear that you have B can be written as this, right? So B prime is again a submodule of B. So if you restrict this map from this B prime, the map G, then you see this is a map from B prime to C, and this is an isomorphism. You can easily see. Uh, that is not very difficult, okay? So you can show it. Okay. Uh, anyway, so and because this is an isomorphism, you have a map from say let's just call this map as G tilde. So now you can inverse this map to go from C to B prime, and then just take the inclusion of B prime to B, right? So this is a map. So you just compose it to H. So H is a map from C to B, and the other condition is almost trivial because that is by definition, right? If you take any, say, x, then what will h of x do? Firstly, it will take to g inverse tilde of x, and this is just the usual inclusion. It will not do anything. But g tilde is same as g. The only thing is that the domain is restricted. So anyway, this g compose g inverse will again give you x. So you get this identity on C. So yeah, there is this. And for the converse part, let's see. So here you have this map from C to B such that uh, this G8 is identity on C. Okay. So to show this is a split exact sequence, you need to find another submodule, right? So you need to show B as direct sum of f of m with something. So you need to find this something, this n prime. And because you have a map from C to B, the most natural thing to consider and the n prime is to take the image of this map H. Firstly, observe this is inside the n prime. And this image of H is the submodule of B. So that is fine. And nextly, let's just show this where n prime is this image of H. So firstly, take any element of B. Let's just take any element this, and then uh, let's write this as this minus of. So what you needed to find this image of F, and yeah. So let's see how you can do it. And also you need to use this. Firstly, you need to find an element which is in image of F and also which is in image of H. Right? Okay. So let's see how we can do. So this is in B, right? And the map G is from B to C. So you can take this G compose H of X. That makes sense. And you can just add it again. Right? Okay. Then, uh, oh no, sorry. I'm just confusing this compositions. I often do this mistake. This should be age, right? Because you are acting G first, so this should be on the right. And this uh, age compose G. Yeah. So clearly this is in N prime, right? Image of age. And this is in image of F because remember this is an exact sequence. So to show this is an image of F, that is same if you just show this is in kernel of G. And that is easy because if you just add G to it, you will get G of x. And then by associative, you get G compose H compose again G of x. But that is just identity, right? That is due to this fact, this assumption. So you get that this is 0, so you are done. I know that. So this is done. And clearly this is a direct sum. You need to show another thing, sorry. I need to show that this image of F intersects image of H. Okay. For that, that is not very difficult because if you take any element, say X, that will be some F of Y and also some H of Z, right? And then just apply G to it. So you get G of X is G of F of Y, but that is 0, right? Because image of F is same as kernel of G, but that is again same as G compose H of Z, and that is identity. So this is Z. So Z you get Z is 0, and if you just apply H to it, you will get H of Z, which is X, and that is 0. That is easy. So yeah, you get B is the direct sum of image of F and some other. Right? This is just the image of H, the map in the other direction. And also due to symmetry, you can again show that there is, see, we showed that there is a map from C to B. But same thing you can take if you take a map from B to A. That is again same. So that can be defined as split exact sequence in an equivalent way, like the way I showed. So I'm not showing it. So the third part will be there exists some say FGH, let's just call K from B to A, such that uh, this K compose F is again identity only. This is exactly same. The proof goes in the same exactly same way. You need to find a suitable candidate for the direct summon, and again you can do it in this way. So I'm just stopping this video here. I'm not going to be talking anything. And in the next video, I will come straight to snake lemma. Maybe I may need at least two videos to complete what is snake lemma. Otherwise, in one video it would be a very long video. So yeah. I will talk about snake lemma and five lemmas, and then I will go back to a free module, or we can talk about tensor. So yeah, let me just stop.